Hello, good morning or afternoon or evening. Can you hear me okay?
Yep.
Yep,
Yes.
loud and clear.
So today the agenda is the Fluid project. Um, is the Fluid team on the call?
Yes, I'm out. I'm here.
Great stuff. Um, I think we'll maybe wait for one more minute, see if other people join, but then I think we're good to go.
It's good.
Great. I think we're good to go. Should we start?
Sure.
Do you have a
Yeah, let me share my screen. 1 second. You guys can see my screen, right?
Yes, we can.
Cool. Right. Let's get started. So first, a quick self-introduction. My name's Sean. I am a committer for the Fluid project, and I was invited by Xin, who I think she's now here today, to give this presentation about the project. So, first, a little bit background about why we have this project.
And sorry to interrupt, just for context, Fluid is currently a sandbox application project and looking to move to incubation, right?
Yes.
Great.
So, okay. Yeah. So a little bit background, as we are seeing in the industry right now, uh, big data applications like Spark and also the AI world are all trying to get themselves on the cloud native platforms, which basically Kubernetes. And according to some survey, I think by 2025, like most of the large scale applications will be on the Kubernetes platform. However, we're facing some challenges here, especially on the data access of this type of applications. First of all, because the computation and storage are basically separated. For example, storage here are no longer attached to the computing resource, and they actually are reside in, for example, S3 or Azure or other object stores. And this type of storage, we know they compared to the local storage, they have much lower bandwidth. So there's a lot of I/O bottleneck here. And especially if the data is cross-zone or even further, then it will be an even larger challenge. And second, with all these different types of storage and then different types of cache systems, we're adding a lot of complexity in managing all the data. For example, if there is like data migration happening in the organization, some data reside in this type in S3, some data reside in, for example, HDFS. Then we have multiple sources. And if this happens a lot, especially when the organization is really large, then different teams may have different preferences. And also there's a lot of cache systems out there which they all behave a little differently. They need different configurations and stuff. So this adds more complexity to the system. And also the computation and the locality of this cache system is not it's not perfect for the computation because um, the resource allocation for them are more like static and they're not locality aware, which leads to some sort of inefficiency. And to give like a very specific example here, in the LL large language model inference scenario, we are seeing when the pods, when a new pod with the image starts, it takes a lot of time just to loading the model. As we can see the example here, it takes 85% of time just to loading the model, and that's around like 4,300 seconds. That's like 40 minutes or 40 minutes or something. So during this time, the pod is doing nothing but reading the model, which is wasting time and wasting the computation resource.
And that is just sort of the cost of pulling the data over slow links or high latency links.
Right, exactly. Yes. So this is why we have Fluid, which is a data and task orchestrator in Kubernetes. This project is launched by Nanjing University, Alibaba Cloud, and Luxio. So it is a middle layer sitting between the data intensive applications, big data and AI, and the storage systems like S3 or HDFS. So a few points of this orchestrator. So first is standardize the data access and distributed cache system in the Kubernetes. It uses the custom resource definition. We'll talk about it later to make the data access in Kubernetes in the cloud native way. Now the second point is it is a extensible framework. It provides an interface for different distributed cache and storage. It is elastic. It is able to scale out and scale in the cache system on demand. It provides a better performance to reading the data. And it also provides some data automation. For example, prefetching, prefetching, migration, scaling, and stuff. And lastly, it is able to schedule the task and data to in a locality aware in a way.
So, just a clarifying question here. So, the plugins and the framework orchestrates, those specific systems like Elluxio or JuiceFS, etc., or is it more generic than that?
So the this runtime included in the image in the graph are the supported ones right now, but it provides the interface to integrate with them so that anyone is able to plug in their cache runtime if they want to. Does that answer your question?
I see. Okay.
Okay, now let's get to the complicated stuff. Okay, so at the bottom is the where the actual data are. NAS or HFS or S3. And then on the left we have the fluid control plane. The gray boxes are belong to the fluid. So we have the operator, which register the CRDs to the Kubernetes API server. And we also have the mutating webhook later on will be used to to schedule stuff. Now, we have two modes here. What first is CSI mode and the other is sidecar mode. Let's talk about the CSI mode first. The operator, the fluid operator, is responsible for creating the cache engine pods. So for example, Elluxio or JuiceFS. After they are there, when application pods are created by the user, it will inform the fluid CSI plugin, which in turn, the operator will create the fuse pod, which basically the fuse pod is able to becoming this bridge for the application pods be able to read the data in the cache engine. So this is the fuse pod. This here is the on-demand pod. Only when the application pods coming in saying I need the data, the fuse pod will start. And when application pods are done, the fuse pods are done. So this is side mode, and sidecar mode is similar. It's just that instead of creating a fuse pod on demand, we use the mutating webhook to inject the fuse container into the application pod. And they talk through a empty directory so that the application pod is able to read the data inside the cache engine. And the fuse sidecar container here is also functioning as the bridge between the cache and application.
Okay. Again, I'm just going to ask a couple of questions just to get things clearer in my head. So basically we have a bunch of data that's available on different storage providers. That could be HDFS, could be S3. And what Fluid is doing is basically automatically injecting a cache layer into the process. And I guess the fuse pod is what abstracts the cache layer. So irrelevant of which cache engine you're using, the fuse pod always presents a directory or a file system via the CSI plugin to the application, right?
Yes, but though the thing is, the fuse pod is not part of Fluid. It's actually part of the cache engine. And then the fuse pod is able to basically expose the cache engine to the POSIX API. So basically, application will then be able to see the data in the POSIX way.
I see. But does that mean that you have sort of one fuse pod per cache engine type?
Yes. So different cache engine have their own um, implementation of Fuse and also different um, like different pod definition. If they, for example, if they need something, for example, maybe Alux will need some different resource in the pod definition than JuiceFS. And Fluid is just the automatic way to create those fuse pods.
I see. Okay. Okay. And I guess the sidecar mode is for applications that aren't using CSI. So effectively you're injecting a way of getting the file system into the application container without having to update the actual application YAML.
Right, right. And sidecar mode is more for the scenario where like CSI is not you can't mix, like you can't use CSI and then you have to use this sidecar mode.
Gotcha. And Raffaele asked the question in chat around if the data is read only.
Okay, this more related to the cache engine implementation. Do they is I believe most of them support write, but only to a certain extent. Like as cache system, they are not storage systems, so uh there's limited support, I guess, for the write. It's not like they can do everything.
Okay.
Then how is access to data controlled from the app pod perspective, not the cache suites? Okay. Um, because um, because it's POSIX API, the access control is kind of from okay, this is mostly my understanding, and the access control is definitely not perfect. Um, the fuse, like the fuse does not impose a very strict access control here, although there are like user group this type of thing. But I think there's always ways to bypass that. And then it's pretty easy for any person to actually read the data. So I think this problem is maybe easier to solve in the cache engine side instead of the fuse side. So although I know you are asking from the application pod perspective, but the actual thing still happens in the cache engine side. So yeah.
But one question then that leads me to, and maybe you might be talking about this later on, but I'll just ask it now. Um, does the abstraction of the different cache engine pods allow the user to define some sort of access policy or something like that that gets configured to the caching engines?
For now, I don't think so, but because the data is divided into different data sets. Uh, for example, let's just say someone is training using the ImageNet, then uh, they just create this ImageNet dataset, and it is effectively separated from other people's dataset. So in that sense, there is some access control, and other people is now able to see what you are using.
Hmm.
Okay, we'll continue here. So this is a flow, a typical flow of how user is able to use the fluid and underlying cache system. So the first step, user will need to create a data set and runtime. Runtime here is just the cache system basically. It will submit the data set CR, and for example here we're using the Alluxio runtime CR. And in the Alluxio runtime CR is mostly the configuration for the cache system. And the dataset CR is mostly what your dataset, like where your dataset is and maybe the credential and stuff. And as long as their name matches, their names match, they know they are they will be bound together. So this two CRs will be submitted to the Kubernetes API server, and the Fluid operator is watching this CRs. So in turn, it will set up the cache system and also create the PVC and PV representing this data set here. Now, after the cache system is up, the user most likely will want to create this data load CR and submit to the API server. And Fluid will then launch this data load job. Here, data load is basically reading the data in the dataset from the remote storage into the cache system. We call this cache warm-up. And the data will basically be read into the cache worker pods from, for example, S3. And now data now is inside the cache system. Then the user will create the application pod with the PVC that was created earlier, mounted into that pod. So then the application pod is able to read from the cache system.
Can I ask a question?
Yep.
Like related to my previous question about the data being read only.
Uh-huh.
So at this point, we have a copy of the data that was in S3, right?
Uh-huh.
And so if something modifies the data in S3, do we get an update?
No.
Okay. And if we modify the data locally in the cache, we don't update S3.
This depends on the implementation of the different cache system.
Okay.
I believe some of them do.
Okay. So this is mostly, and then I'm just trying to understand, but this is mostly for immutable data that you need to bring to a local compute, let's say.
This is one. I would say this is one of the most common use case. Read only from the remote storage, but Yeah, well, this is one of the most commonly used case. But if
Understood.
I mean, there are certainly there are users who, for example, maybe write some checkpoints in the middle of the training, for the
Okay.
cache, the S3. But those type of stuff really depends on whether the underlying cache system supports.
Okay, thank you.
Now, there are quite a few runtime cache engine being supported, and we'll use different CRD name to differentiate different cache systems, and they're all in the same. The interface looks the same. And for example, on the right side, we have different runtime like Jindu runtime and Luxor runtime, and most parts look very similar, like the cache configuration, like pod resources configuration, pod affinity. Only down in the properties for specific runtime, their specific configuration name and stuff will look different. So this significantly unified and standardized the cache runtime configuration model. Now for the data automation, here we are talking about mostly data load, data migration. We have this data set custom resource responsible for that. For example, on the left side, we named the data set to Spark, and of course also the namespace in the Kubernetes cluster. We can also specify some automated jobs. For example, this is a cron job, which will read the data every 10 minutes. Basically, like read the data from remote storage into the cache system every 10 minutes. And then the target here is where the data is. And also, we can also specify the number of replicas we want in the cache system.
I think there's a question around what happens when the data is too big to fit into the cache. And
okay, when the data is too big to fit in the then well, the only part of the data will be in the cache, and the rest are still in the remote storage. And is the cache only available to the pod running on that node, or will the cache be shared across nodes? It will be shared across nodes. So for example, if you have 5 pods doing the training, and all on different machines, let's say, and well, it doesn't really matter, but you can basically have the cache system in the same Kubernetes cluster, but all on the different nodes. And then these training nodes still are able to read the data from the cache engine, although they are not on the same machine. But they are. Then the process will be like the application sending requests to the fuse pods, and the fuse process will read the data across the network to the distributed cache system to get the data back to the application pod.
Right. So just to summarize, in case it wasn't obvious, like the distribution of the cache is an attribute of the caching system itself, right? So systems like Alluxio allow you to create a distributed cache over multiple nodes anyway, right?
Yeah.
Right.
Okay, now let's talk about the elasticity of the cache system. So we have different, so this is mostly for scaling purpose. For example, when when a lot of, well, when you need, sorry, let me rephrase this. When there are a lot of requests coming in and then you need to spawn a lot of pods in a very in a short time, you will want to scale more pods so that to reduce the application latency. So we have a few ways for scaling. Manually, basically, it's just type in the kubectl command. That's the most basic way. Yeah, you can also have a cron job. For example, if your use case is specific for some type of work that happens only at a certain time, for example, maybe 2 a.m. the system will trigger this job to do something, do some analytics and stuff. So you know at 2 a.m. there will be a lot of requests coming in. So you can basically create this cron job, say, oh, at 2 a.m. or like 1:50 a.m. I want more cache pods. And the third way will be based on the custom metrics. For example, I think on the right side is one of the examples. Here we are saying when the capacity use rate metric reaches 90%, then we will scale up our cache pod. Let's see. Now, why this is important in the use cases. This is one example for the LLMs. This is a problem that we saw earlier too, that the storage bandwidth is limiting the cold start in the inference scenario. Basically, if the bucket has like a 10 gigabits per second bandwidth, it will be the reading is slower. But if you have more cache pods and they are all reading the same, they are all reading the same, in this case, the model, you are effectively distributing this one job to, say, 5 or 10 clients. So, but they are all reading, they only keep one copy. Now with more clients, we basically get like a much higher bandwidth. For example, in the graph down here, this is reading 30 gigabytes data from OSS. If you directly read from OSS, it takes 2,500 seconds. But if you have 5 clients or even 10 clients, we're basically 5 times or 10 times faster than just one single client reading from the OSS. So now, let me close the bridge here. So if we have 10 hash pods here, they put in the same model at the same time. They distributed this model basically into 10 clients, and they construct a single model. It only takes 1/10 of a time to read this model. And later on, when application pod comes in, they can read from the cache system instead of reading from the OSS. So we not only save the time of reading directly from OSS, which is slow, but when we have multiple clients reading from OSS during the warm-up phase, it is also much faster.
So can I ask maybe a clarifying question? Because I want to better understand sort of the scope of the project. You know, the speed up that you're seeing there is not because of Fluid per se, but it's because of the caching system, right? So it's
right.
So sort of, you know, that's a feature of, say, something like Elluxio, for example.
Right.
So, you know, the way I'm looking at this is Fluid is doing sort of the clever orchestration of Elluxio and making it easy to bind the application pods to the cache in a transparent manner. But I guess, you know, one of my questions would be, how much of this functionality might already be in the caching system? So for example, you know, there's a system like Elluxio, and I'm just picking Elluxio just because it happens to be the first one in your list. You know, does a system like Elluxio have its own operators that can do a lot of this orchestration itself? So where does Fluid fit in, and why would an Elluxio user use Fluid to configure their cache?
So yes, I believe most of, if not all of them, most of them have their own way of managing themselves on Kubernetes. The Fluid, well, first of all, Fluid was created much earlier than when they start on Kubernetes, and then from the user, from the let's say data scientist perspective, or from the Kubernetes team people's perspective, they don't have to go inside details about how Elluxio works, or how say JuiceFS works in detail. With the Fluid interface is more intuitive than what the cache system is able to offer. For example, the dataset concept fits more close to the end users.
I see. But sort of, isn't there a risk that at the end of the day, if the caching providers continue to refine and improve their operators, that sort of end users might prefer to just use the native operators rather than something like Fluid?
Yeah, I mean, it's definitely possible, but with this with Fluid, basically also avoid the vendor lock-in. Basically, you are free to switch to another cache engine and without too much problems. But if you are attached
Right.
to one of them, then it might be hard because they have different, different ways of setting up the whole thing on Kubernetes.
Right. Okay.
So for then for oh yeah, this is an well yeah, let's talk about the cache aware scheduling. This is a way to basically schedule your is a way to enable the user to schedule your computing task as close to the data set as possible. For example, here if you have dataset A in zone A and dataset B in zone B, when you schedule your compute pod, for example, here, this pod definition on the left, say you are using the dataset A, the Fluid will help you to schedule this pod as close to dataset A as possible. So first it will try to make sure it's in the zone A, and then it will try to make sure your pod is actually on the same node as where your data is. Now, this may not always be the case. For example, you may want to schedule your computation to a specific node, for example, GPU node. Then we will also honor that. We will not force you to schedule your compute pod to the same node as the storage to the cache, which is why here is like the preferred, if not the required. I think that's mostly for the technical details about Fluid. In terms of cloud native alignments, we also have a lot of integration with other CNSF projects. We list a few of them here, including Prometheus, Grafana, Kserve, Knative, and other projects. And we want to make ourselves a vendor neutral distributed cache platform that making different cache systems to be resilient, manageable, and observable on Kubernetes clusters.
Can you comment on the difference with KubeFS? I know they've invested a lot into their caching of multiple clouds.
So KubeFS is the actual cache system which is able to say read the data and serve the data to the applications, whereas Fluid is more like the orchestrator of different cache systems to manage them on the Kubernetes cluster. Fluid itself doesn't have this data caching system.
So you would envision a plugin or using them
Yes.
sometime in the future? Because I don't think I saw that on your list.
Yeah, for KubeFS, I'm actually not sure. I probably need to double check on that.
Let me ask a couple of clarifying questions on this. So first off, do you see in your use cases that an end user might be using multiple cache providers in their environment, or would they be typically standardized on one?
From what I'm seeing, most most of them are using one, but sometimes during the POC phase, they might want to try different systems to pick the one that fit their scenario better, or like say
Okay.
hyper performance or easier usage and stuff.
Okay. And then the second question is, who contributes the code for the cache system provider? So you know, there's an operator or some sort of support for each of the specific caches. Is that something that the Fluid group or the Fluid project is maintaining, or are the cache providers also contributing to Fluid?
Actually, well, I think different different cache providers are a little different. I know some of them are contributing to the Fluid projects. If I remember correctly, like JuiceFS, they have their maintainer in the Fluid community, so they will actually have people to integrate JuiceFS with Fluid.
Right, but sorry. Look, what I'm trying to get to is, how do you keep up with sort of the changes in the different projects and the different caching systems, and making sure that Fluid can continue to remain, you know, compatible with different versions of the cache providers and things like that?
I see. Well, so first, apparently we don't want them to break the backward compatibility. That's for sure. So when so, but what if they have to um. Well, it's still it's still down to different cache engines, I think. In some of them, if anything happens, they will contact Fluid saying, "Oh, we made this change, and we might need to modify the Fluid a little bit to making sure this new version works." And the discussion there will be this discussion, and they'll see who will be responsible for making this change. Most of times, this is not like a huge change or stuff.
Okay.
Okay. Oh, this is the community growth since we entered Sandbox in April 2021, and we can see there's we have stars from growth from 200 to 1600, forks from 20 to more than 700, and we have a lot of more contributors, a lot more commits, and we have 7 maintainers from five organizations and 25 committers from 15 organizations. There are also a lot more companies contributing to the Fluid project. And a lot of different industries are using Fluid. Most of them using Fluid for data access acceleration, and also like cache elastic scaling, and also the scheduling. It is also integrated into a few cloud providers in especially in the China region, like Alibaba Cloud, Tencent Cloud, and Baidu Cloud all already provide this cloud native cache service based on Fluid. This is like a very specific use case example. I don't know if the time allows me to like explain this into details. Yeah, there are two very specific use case here. Well, maybe I can just go over them real quick. So the challenge here is reading small files from OSS is slow. That's basically the most important problem here. So using Fluid as a cache system, we are able to reduce their training time by 20% because now they don't have to always read the small files from OSS object store. They can read directly from the cache system, which in turn also improve their GPU utilization and also because the Fluid also provides the fuse auto recovery, and they now have a better availability on the training jobs. And for this MetaBit trading company, what we're seeing is they don't have a lot of data, but when they need to use the data, there will be a huge amount of pods start simultaneously and try to pull the data. So instead of them reading from the remote storage at the same time, reading from the cache system provides them a lot of benefits. They see like a 40% time saving here. And also another benefit here will be cost saving because reading from object store every class will incur some cost, but apparently reading from cache system doesn't incur that. We only read from the cache system only read from the underlying storage system once, instead of like hundreds or thousands of times.
And again, just to ask a quick clarifying question, and I know we're coming close to time, but the benefits that you mentioned here, are they benefits of Fluid or benefits of just using JuiceFS? Because
yeah, so the performance and cost saving is mostly from the underlying cache system. Yeah.
So what are the benefits of so because this is important if you're applying for incubation, what is the benefit of Fluid in these use cases? Like why did they choose Fluid rather than, for example, using a native operator, for example? Or put another way, take that last use case that you were showing on the screen before, the MetaTrade, I think it was called, or MetaBit trading. Why did they choose to use Fluid with JuiceFS and not just use JuiceFS on its own?
Good question. I'm actually not sure about that. Yeah, I don't want to give like my wrong information here, but maybe because there's very close integration between Fluid and JuiceFS. Maybe Fluid is probably the operator for JuiceFS.
Okay, that kind of makes sense. So you know, JuiceFS are contributing to Fluid, and in the case of JuiceFS, then Fluid, I guess, is the primary operator because
Yeah.
JuiceFS aren't building their own. Okay, and that kind of makes sense because the JuiceFS maintainer is on is one of the maintainers.
Yeah.
But what about the other ones? You know, so you know, take the case of Aluxio or something else.
Um,
Why would somebody just use Aluxio and choose to use Fluid?
There's also I think the reason also lies inside because Fluid is like incorporated with the cloud. Like for example, if some company is already using Alibaba Cloud, and they can use this already is provided by Alibaba Cloud to easily integrate Fluid into their system. Maybe it's just like a simple
I see.
one button. Do you want to use like cash system? Maybe yeah. But if they need to use, for example, Luxio, they need to contact Luxio or figure out a lot of things, set up all the stuff by themselves. That's a lot more complicated.
I see.
Yeah, I think that's another reason. Yeah.
I think as part of the incubation, like one bit of feedback here is part of the incubation application. It's important to kind of summarize what the benefits of Fluid are and why end users are adopting Fluid. Because, you know, and it's important not to sort of mention like for you know there are the obvious benefits of implementing the cache system.
Yeah. Gotcha.
But Fluid is not the cache system. Fluid is how you abstract the cache system, and it gives you the ability to use the cache systems in different clouds in different ways, and it allows you to, you know, in some cases, you know, some cache systems like JuiceFS might be developing Fluid as their primary operator, right? And I think I think you need to highlight those clearer.
Yeah, I see your point. We are, I think, already time, and yeah, the rest is not not super important.
All right.
Yeah, thanks for the feedback.
This was a really good presentation. Would it be possible to share the link to the presentation, please?
Sure. How should I send this out? Like,
if you send us the link, you can send me the link on Slack or send Xing the link, and we'll add it into the minutes, so that way we can.
Okay. Yeah, sounds good.
Great stuff. Well, thank you again for coming to present. I think this is an interesting project, and thanks everybody for joining our tag call. We're at time now, so I think we can call it a day for today. Thanks again.
Everyone.
Thank you. Bye-bye.
Bye.